is Hogancamp from the USC, and we will talk about categorical diagonalization.
All right, thank you. Thank you for the invitation. It's been a lovely semester and an excellent conference. Okay, so today I want to talk about work with Ben Elias, which in a slightly different universe would have appeared on the archive this morning, but will actually probably appear in the archive like 2 days from now. Anyway, it's very, very close to being finished or posted on the archive. Okay, so what do I want to talk about? So this conference is sort of all about categorification. So let me first, provide some motivation for the sorts of questions I want to ask. So the goal, one goal that we might have as categorification theorists is we want to categorify linear algebra, just elements of linear algebra, whether it be Hecke algebras or all of representation theory or whatever. Particularly relevant for this conference is we want to apply such things, such categorifications, to the study of higher representation theory, so categorified representations of braid groups or Hecke algebras or quantum groups or whatever. I mean, so for instance, diagonalization is sort of an important, like to say it's an important tool is kind of an understatement, but it's an important tool in representation theory. So you might imagine some kind of categorical analog of it to be important in higher representation theory. And also categorified, for instance, categorified quantum invariants of, say, links in the three-sphere or maybe eventually three manifolds. For instance, if you know the construction of the colored Jones polynomial or colored Reshtigan-Turaev invariants, you know that an important role is played by certain idempotents in Hecke algebras or whatever, and categorification of those gives categorified colored invariants and so on. So I want to focus today on the categorification of idempotents. And I want to view categorical diagonalization as a machine for producing such objects, and also not just producing them, but understanding their structure. I never remember how it goes. Should I write on this board next? Whatever. Okay. Okay. So, and then, right. So let me give you an example of a sort of an algebra and some idempotents that we might want to categorify. So we have the Hecke algebra on two strands. Sorry, Hecke algebra H2 is by definition the algebra, let's say coefficients are rational functions in Q with a single generator modulo the relation that modulo this relation. Some people have different conventions. This is fine. I'm not going to go into enough detail for it to matter. Then we have some special idempotents in here, which are indexed by partitions. So there's this guy. And this guy. And in fact, the defining relation in the Hecke algebra is telling me that T is diagonalizable, and these are its eigenvalues, for example. And these are sort of the eigenprojections onto the eigenspaces, if you like. So these are some idempotents that we might want to categorify. But let me state some philosophy. I'll come back to that board in a second. The philosophy here, though, the kind of questions we want to ask is we don't just want to categorify idempotents, we want to do more than that. We want to categorify sort of whole picture. So suppose we're given some algebra. For instance, in my example, the algebra was H2. If we have an idempotent, so experience shows that to categorify idempotents, like actual idempotents, by the way, what does an idempotent mean? An idempotent satisfies the relation p squared equals p. To categorify that relation often requires infinite complexes of some sort. Okay. So for instance, these two guys have denominators, and to categorify them, you imagine expanding the denominator in some geometric series, and then you have some infinite thing that you have to categorify. So the categorifications of these guys tend to be infinite, complexes or something. And sometimes we don't like infinite complexes. So observe, though, a lot of times we can clear denominators in some sense. So a lot of times we can find a scalar alpha, so that when we multiply our idempotent by this scalar, we land in some integral form. So we want to not just categorify the idempotents, but we want to categorify what I'll call the integral forms of the idempotents, which are some scalar multiples that lie in some integral form. So these will be quasi-idempotent, meaning that if you take a scalar multiple of an idempotent and square it, then you'll get a scalar multiple of. So when you rescale idempotents, you get, by definition, quasi-idempotents. And you want to categorify these guys with potentially finite complexes. And you also want to categorify the relationship between them. So you want to understand how multiplication and division look. So for example, here are some idempotents I may want to categorify. I'll denote their sort of integral forms. Like so. I've just cleared the denominator by multiplying by the appropriate scalar, and then you could hope to categorify those with finite complexes. Okay, so that's the sort of recurring theme, is that you don't want to just categorify the idempotents or the quasi-idempotents. You want to do both and understand the relationship between them. And this relationship will end up being something like causal duality between polynomial and exterior rings. If you know what that means, then you know already that it converts infinite things to finite things, because polynomial rings are infinite and exterior rings are finite. If you don't know what that means, don't worry about it. Okay, but let me just say, again, a little bit of philosophy is sometimes to categorify these, there are some formal constructions that imply existence of these complexes. So for instance, Rosansky constructed some categorifications of the Jones-Ventral idempotents by taking sort of an infinite power of the full twist braid acting on, Barnardton's category. So sometimes there are some formal constructions that imply the existence of such things, but you have no idea what sort of structure they have until you construct some kind of finite version of them. And I'm going to do some examples illustrating all of this stuff. Okay, but that's the motivation. Cool? Okay. So categorical diagonalization will produce not just idempotents, but the finite ones as well. Okay. So before I start talking about categorical diagonalization, I should tell you what idempotents look like when you should tell you what idempotents in category theory look like. Oh, sorry, I didn't even write this, but it's kind of important. One of the reasons we don't like infinite complexes is because if we use them to define colored homologies, then those colored homologies can't be functorial for formal reasons. You want the invariant of the unknot. Sorry, if you don't know what this means, then ignore it. But if you do know what this means, then don't. When you define a colored homology by one of these constructions where you define an idempotent and then color your link with an idempotent and whatever, the homology of the unknot is typically the endomorphism ring of that idempotent, which if it's infinite dimensional, will obstruct the functoriality of that knot invariant. To have a functorial knot invariant, you need a Frobenius algebra there, and Frobenius algebras are finite dimensional. Okay. However, if you color them instead with the quasi-idempotent relative, then you're good to go. Okay. All right, so we hope to get functorial invariants from the finite things is the main reason we might care from the topological perspective. All right, so what's the kind of thing I'm going to be working with? So let A be a category. And I want to be able to do linear algebra. So I need various structures. I need a direct sum. So this is going to be an additive category. I need a tensor product. So this is going to be like an analog of a ring. I want it to be an analog of a unidal ring. So I'll have a monoidal identity. I also want mapping cones. So it has a mapping cone construction and suspension and a functor. So this is, well, captured. I'll call it a triangulated monoidal category, but I realize not everyone. It's even hard to find a definition of such things in the literature. So let me just give you an example. Category. So example. You could choose your favorite ring and let A be the homotopy category of complexes of bimodules. Maybe finitely generated, who cares? Maybe some subcategory thereof. But anyway, the point is you have the suspension functor here is just the homological grading shift in the homotopy category. The mapping cone construction is the usual mapping cone for chain complexes. And, you know, the monoidal identity is just R, the trivial bimodule, thought of as a chain complex in degree 0. And then you know how to tensor chain complexes because you know how to tensor bimodules. So the tensor product here is tensor product over R. Okay, so that's the example you should have in mind. For example, Soergel bimodules will be of this flavor. Now, idempotents in this setting come in two flavors. I want to start off with this, even though it's a little bit abstract and a little bit technical, because it's important. And sort of is the ultimate reason for various other strange things that happen later. There are two flavors of idempotents. There's unidal and co-unidal. Definition: a unidal idempotent in A is an object. I'll use capital letters. So capital P in A, together with a morphism called a unit map. I'll call eta, such that eta tensor the identity on P. Well, where does it go? It goes from 1 tensor P to P tensor P. And then also the other way around. are isomorphisms in A. So a very weak categorification of the notion of an idempotent is an object P so that P squared equals P, or is isomorphic to P. But that's really weak. Like for instance, when you define a monoidal category, you don't just say that the tensor product is associative up to isomorphism. You pick the associator and you say, here's the associator, and it satisfies some relations. So this is kind of an analogous thing. I'm not saying P squared is isomorphic to P. I'm saying there is this structure map that gives me the isomorphism. That's a very important distinction. Okay, and there's also a co-unidal idempotent, which is the obvious modification. You can fill in the blanks. Let me go ahead and define something else, which this is maybe not the right place for, but I'll do it anyway. Locally, so these are not all the idempotent, you have chocolate and vanilla, and you can also do swirls with them. So this is a co-unidal and unidal mixture. So a locally unidal idempotent is anything of the form P tensor Q, where P is co-unidal and Q is unidal, and P and Q commute. They tensor commute up to isomorphism. You can convince yourself that if P and Q commute, then such an object will be idempotent. And this is like saying that in topology, the definition of a locally closed set is something that's the intersection of a closed set and an open set. So you can kind of think of these as being like closed and these as open, and tensoring them as like intersection. Yeah?
Can you always go from a unidal to a co-unidal by taking a cone? Can you always switch from co-unidal to unidal by taking a cone?
Yes. So exactly. So every unidal idempotent will have a co-unidal complement. So decategorified, you have this construction which is 1 minus E. So if E is an idempotent, then 1 minus E is its complement. And then the categorical analog is taking the cone on that. And I'll say that more explicitly in a second. Yeah. All right, so what are my favorite examples? Let me not erase that just yet. So here's my favorite example, and this is going to be a running example for us throughout the talk. So let's let H be the group algebra of Z2. I guess I could probably do this integrally, but let me not do that. Who cares? So H is this guy, and then A is going to be the homotopic category of complexes of H modules. H modules. And I'm putting a minus sign here because I want to allow infinite complexes. Okay, I want to illustrate the necessity of infinite complexes in this example. So let me choose this category. If you take a second to think about it, the tensor product is still well defined here. Because if you take two semi-infinite complexes and tensor them, the relevant direct sums will all still be finite. And you know how to tensor H modules because this is a group algebra. If you take two H modules, if you have an endomorphism X here and there, then you get an endomorphism, which is their tensor product there. And okay, so the monoidal identity is the trivial module on which X acts by 1. The monoidal tensor product is literally a tensor product over Q, and so on. And what are my examples I want to do? So let's define Q to be the following thing. So I'll underline the term in homological degree 0. There's a canonical map here that sends x to 1 and 1 to 1. And the kernel of that map is 1 minus x. The kernel of that map is 1 plus x. Okay, so you just alternate from here on out. And let me define P to be its complement. So decategorified, the complement is obtained from the original by subtracting 1 or whatever. And so categorically, I'm going to subtract 1 to get the complement of this thing. Okay, so those are my complexes. And now I want to observe that Q is acyclic. Okay, so it's acyclic and kills projectives. In fact, every acyclic complex is going to kill projectives. And P is projective and kills acyclics. It might bother some of you that I'm saying this is acyclic. So you might be thinking, well, acyclic complexes are supposed to be 0, right? Wrong. Okay, so I'm working in the homotopy category of H modules, not the derived category of H modules. So this thing is acyclic, which means it corresponds to an exact sequence, but it is not contractible, meaning it's not split exact. Okay, however, if you're split exact and projective, then you're 0. So that's why these guys are kind of orthogonal to one another. Anyway, so that's some observation. Second observation is that they fit into a distinguished triangle that captures the fact that this one is basically that one together with the extra term. So how does this go? I guess this guy has a map to 1. And this guy has a map from 1, which is the inclusion of that last term. And then this one, if you notice the relative shift, there's actually a map, from here to here, which is the quotient map. Except that it has a shift, and that's a distinguished triangle. Okay, and this relationship is the categorical analog of being complementary idempotents.
Which one of these is unital?
The one with the map from 1, so Q. So let me go ahead and give that a definition real quick. A pair of complementary idempotents in A, whatever A is a pair of objects, P and a Q, such that one, they annihilate each other with respect to the tensor product. And secondly, there exists a distinguished triangle like that. Should I write it again? Maybe I will. So P goes to 1, goes to Q, goes to P. Just a brief remark. So I'll maybe call this map epsilon and this map eta and this map delta. Such a distinguished triangle is actually determined up to unique isomorphism by either P or Q. So consequently, an idempotent uniquely determines its complement, like it should. And I don't really have to include the structure maps epsilon, eta, delta in my definition. They exist, and they're unique up to some kind of canonical equivalence. Okay, Great. So there's this sort of dichotomy between categorical idempotents. You have a unital one and a co-unital one. I'm going to come back to that in time. Okay. What about the finite the finite complex? Okay. So let me say something about this. So here's an infinite complex. What might I mean by a finite version of it? Well, I might mean just a finite complex that's acyclic. So finite version. So let's go back to that example, and let's define what will be the finite version of Q. So let me call it K sub Q, I guess. Let's define it to be this thing. So we have the canonical map from H to 1. We have the kernel of that, which is 1 minus x, and then we have a map here that sends 1 to 1 plus x. Observe. K is acyclic. So, right, I don't know, this has dimension 2, this has dimension 2. It's easy to see the rank of this is 1, the rank of this is 1, and the rank of this is 1, whatever. Okay, so what does this mean? So since it's acyclic, it's actually annihilated by P, because P tensor it will be acyclic and projective. And since you annihilate P, you absorb the complement. Okay, so that's interesting. What's the actual relationship between? So I want to understand the relationship. So, sorry, I'm not saying this clearly. So we've categorified the idempotent. We have something I'm claiming is like a scalar multiple of that idempotent and is also finite. But what is the relationship between them, multiplication and division? So let me explain that in just a couple words. So what happens if you take this expression and expand K using this description? So this is actually the total complex of a bicomplex. You sort of distribute K. You know, in previous talks, I thought about calling this section complex arithmetic, because it's arithmetic with complexes. Okay, so this guy is 0, because acyclic tensor projective is 0. This guy is also 0 for the same reason. So when you cancel both of those terms, you get something which is homotopy equivalent to a Q and a Q with some induced map between them. And let me remember the degree shifts. So this is in degree 0, minus 1, minus 2, minus 3, and what did I do? Ah, thank you. Thank you. And so this is actually the cone on a map from Q to Q. Do you guys believe that? Exercise. Construct an endomorphism from Q to itself, whose mapping cone is that thing. Well, it's periodic, so you have an actual like periodicity endomorphism. That's what this is.
K an idempotent? Is K an idempotent?
K is quasi-idempotent. So if you tensor with itself, you actually get 2 copies of K. In fact, this is like the Kojoule complex on some endomorphism of Q.
You have axioms for quasi-idempotent?
Yes. Well, maybe not. Yeah. It's better to characterize them via their relationship with the idempotent. Okay. Anyway, so that's how you. This is the kind of categorical analog of multiplication. See, I have 2 copies of Q, and K is their, difference. No, okay. Is that okay? All right. Now, what is the analog of division? So how might I construct Q in terms of K? So last bullet point in this sequence of observations is, well, if I want Q from K, I should look at this picture. So I just string together infinitely many copies of K. And I get some big chain complex. So in degree 0, I have that guy. In degree -1, I have that guy. In degree -2, I have the sum of those two things, and so on. And then if I put, I don't know, identity here, I can cancel them by some Gaussian eliminations, and then I get exactly that expression for Q. So this is what division and multiplication look like in this context. Cool? Okay, and that's what categorical, these are the sorts of things that categorical diagonalization will produce. In fact, this is a special case of categorical diagonalization. And furthermore, this is very close to the examples I wrote down at the beginning up there, where I have two eigenvalues and the projections look like that. So somehow all these examples are like the same example. Okay. Okay, so what about actual categorical diagonalization? Let me stop stalling. Okay. So let's return to this example, or at least something formally very similar and more general. And I want to illustrate what categorical diagonalization looks like for two eigenvalues. So this is, the way I think the rest of the talk is going to go is I want to tell you something of what the general theory of diagonalization kind of looks like. And then at the end, if I have time, which I almost never do, I want to reserve time at the end, so I'll cut off things as I have to tell you about the actual categorified Young symmetrizer. So the main application of this theory, just so you don't kind of, so we can tether ourselves back to reality, the main application is to the diagonalization of the full twist Rouquier complex. So on the Soergel category, which was introduced and discussed heavily in the last talk, we have this braid group action. So we have Rouquier complexes for each braid. Tensoring with them, you can think of as being endofunctors of that thing. And the main application of this whole big theory that I'm kind of giving you snapshots of, the main application is to diagonalize the full twist braid, acting on the Soergel category. And the eigenprojections there that we produce are categorified Young symmetrizers, which play a huge role in, not invariants, but also this connection with the Gorski-Naguts-Rasmussen picture. So the full twist in their picture is just 01. Anyway, there's a very beautiful correspondence which I could probably deserve 6 lectures instead of 1, but I'll do what I can. Okay. But I think it's important to understand the construction for two eigenvalues because it's pretty, and it actually illustrates a lot of the general theory. Sorry, two eigenvalues. So let's consider a linear algebra situation where I have, say, K is a field or something, A is a K algebra. I have scalars lambda and 1 and lambda 2, which are in K, and I have a given element in A. What does it mean for F to be diagonalizable with these two eigenvalues? Well, for starters, we should have this identity. So So recall, so for instance, if A is the algebra of endomorphisms of a vector space, this is the usual sort of minimal polynomial condition for being diagonalizable. And let's assume that these are not equal. Then how do I prove that f is diagonalizable? I mean, so what does it mean for f to be diagonalizable? It means I can construct projections onto the eigenspaces. So let me actually construct the idempotents from f and its eigenvalues. So P1, let's say, is this guy, sorry, lambda 2. And P2 will be given by the same formula. Some observations about these things. First off, they add up to 1. It's an easy check. Second off, Pi kills f minus lambda I, because the numerator already kills f minus lambda I by hypothesis. I don't know why I wrote this. Sorry. And consequently, P1 and P2 are orthogonal. And then once you know that they're orthogonal and then they add up to 1, they're automatically idempotent. Okay? Ah, sorry, I'm forgetting stuff. Okay, so these are the projections onto the eigenspaces for f. How do you categorify that? So now, in the categorified linear algebra, whatever, so we have A, some triangulated category, triangulated monoidal category, or whatever. Let's simplify things a little bit by saying that it's a homotypic category, something. I don't want to. This works, of course, in more generality, but then we specialize a little bit for the sake of concreteness. Suppose I have a chain complex of bimodules, and suppose I have scalar objects. Well, what is a scalar object? Well, a scalar object for our purposes will just be something that's like isomorphic to a direct sum of shifted copies of the identity. So scalars are things like 1, and 1 plus 1, and 1 plus 1 plus 1, and shifts of those, and so on. I also want to assume they're scalars. So for instance, this means they are just actual shifts of the identity. Instead of sums of shifts of the identity. And assume that we have maps. So I need to categorify these differences here, which, if you're in the business, you know, means I need to be taking some kind of mapping cone. So a natural thing to do is to say I have a map from lambda 1 to f, and from lambda 2 to f. Oh, sorry. I called them lambda and mu. Let me call them lambda 1 and lambda 2. And the sort of categorical analog of this equation is the following equivalence. Suppose that when I take the cone on alpha 1 and I center it with the cone on alpha 2, I get something contractible. There's something funky in linear algebra, which is if you have something, a mapping cone, which is constructed from f and then the identity, and some other guy, which is constructed from the same sorts of objects, they don't need to commute with one another. Which is terrible, because in linear algebra you want to know you have statements like polynomials in f commute with other polynomials in f. But categorified, that's like just not true. So I want to assume they vanish in the other order as well. Okay. Okay, and what are the analogs of the eigenprojections? So I want to categorify these formulas. And let me just do it over here. Gosh, let me do it here, in fact. Man, I don't have any good places to do it. Just here, why not? Okay, so the projections are going to be, so define P2 to be the kind of total complex of this crazy diagram. So I want to construct some infinite chain complex constructed from F and the scalar objects lambda 1 and lambda 2 and the maps alpha I, and then I want to convince you that it's going to be an idempotent and that it projects onto the, I don't know, eigen category corresponding to alpha I. Okay, so that's my task. And then my task is to convince you that it can be done in more generality. Okay, so here we go. I don't want to make a mistake here, so since these are invertible, I have 1 over lambda 2. That's like if lambda 2 is a shifted copy of the identity, then 1 over lambda 2 is the thing with the negated shift. Okay, so now I can apply that to F. And then I have lambda 1 over lambda 2 F, and then lambda 1 over lambda 2 squared F. Oh, sorry, that's not supposed to be an F. So P2 is going to start. So remember, what is the numerator of P2 here? P2, the numerator is F minus lambda 1. So what I can do is I can put a alpha 1 there. And that will take me from this scalar thing to this shifted copy of F. And then I can do an alpha 2 here, and an alpha 1 here, and then so on. I can repeat. Let me put a sign here, because I'm OCD like that. So there will be signs, and not that it matters. Okay, what's P1 going to look like? I'm going to give you a couple seconds to guess. I want P1 and P2 to be complementary, which means I want their difference, quote unquote, to be 1. Or sorry, their sum should be 1. Okay, so it's going to be the exact same picture with an extra copy of 1 somewhere. Duh. No, I shouldn't say duh, but okay. So this is kind of the only thing you can do. It makes sense, and in fact, it works. And now this one starts with an alpha 2, maybe minus. This one starts with an alpha 1, and this one starts with an alpha 2 minus. And then they repeat. Okay? So that's the construction. And what can we prove about? What can we just observe about these crazy things? First thing we observe is that they may not actually make sense. Because they're infinite complexes, and you have to check that you have some kind of like infinite direct sums in your category or whatever. But let's not bother with that for now. Do you observe anything? Well, what was the argument that we had here? We first argued that their sum of these things was 1. And in what sense is the sum of those two guys 1? Not literally a direct sum of them is 1, but there's an extension. So observation, there exists a distinguished triangle. Which way does it go? Well, you know, I was a little bit sloppy with grading shifts. So I'll underline the term. When you form the total complex of this thing, look, it's actually a mapping cone, because the top row maps to the bottom row entirely. So I only ever have maps from the top row to the bottom row. So this is literally a mapping cone. Same thing with the top dude. The top row maps only to the bottom row. And so it's not some crazy total complex of a bicomplex. It's actually just a mapping cone. And I have to specify the homological shifts by underlining some terms. So I'll put these unshifted, and I'll put these unshifted. And so now it's clear that P1 has a map to 1, and P2 has a map from 1, and then there's a map like this, which makes it a distinguished triangle. The next thing I proved decategorified was that Pi annihilates this difference. So how do we see that categorically? Well, check it out. By hypothesis, conon alpha 1 and conon alpha 2 annihilate one another. And P1 is basically a filtered complex where the subquotients are conon alpha 2. So if you sort of reassociate this guy according to the southeast diagonals, you get a chain complex that's constructed from just cones on alpha 2s. And meanwhile, alpha 2 is orthogonal to alpha 1, so you get contractible. I'm lying to you here a little bit, so I'll come back to why I'm lying to you. And the same argument works for P2 and alpha 2. So consequently, P1 and alpha 2 are orthogonal, and consequently they are complementary idempotents by definition. Okay, so that's the kind of construction. So this is saying that they add up to 1, kind of categorically. This is saying they're orthogonal. This is saying they sort of project onto the alpha I eigencategory, whatever that means. And the consequence from these observations that actually they're idempotent. Okay, I'm lying a little bit. I don't want to go into the technical details here, but we need some kind of local finiteness. So for example, so the way I've defined things, A is this category of bounded above complexes. And so for example, the sort of thing that makes this go through is if I assume that what are my denominators? My denominators are all like lambda 1 over lambda 2 to some huge power. And this construction will make sense if those tend to minus infinity. Okay. Anyway, but if you assume this, then that means these constructions are like all locally finite, which means they're finite in each homological degree. And then all of these crazy infinite simplifications that you do here actually make sense. And that's important. So I want to just observe that there's a kind of order on the eigenvalues that has appeared, which is not clear decategorified. P2 maps to P1, not the other way around. Okay, that's important. And now, okay, so let me state the diagonalization theorem now that I've given you an explicit example of it. And then maybe state the application to Soergel bimodules. And that's probably all I have time for. Wait, when did I start?
Yeah, you have 12 minutes left.
12 minutes. Okay, good. Okay, well. Okay, are there questions up to this point? I know it's a little heavy on that. Oh, yeah.
But if you exchange lambda 1 and lambda 2 and Pi 1 and P2, they will be also exchanged, or is it?
Yes. Yeah, so maybe I should do this example real quick. This is actually a special case. This Q that I've written here is actually a special case of, well, it's unidal, so it's a special case of P2. So this guy here, I'm being sloppy because I don't have a lot of time, but let me call this F. I'll just put little circles around it everywhere. So in this example that I had, this running example, I can call this one alpha. So this little piece of my big chain complex that I'm calling Q is actually a chain map from 1 into F. So I can call that alpha 1. And this is alpha 2. Sorry, this is way too sloppy. Let me just say that going back to the running example, I could choose F to be this chain complex and alpha 1 to be this chain map, which just sort of includes, it kind of maps 1 into the kind of tail end of this thing. And then alpha 2 is the other guy that maps 1 into the head. Okay. So this maps from just 1 with no shift into F. And then if you play this game with those two maps and this F, you get exactly this chain complex. But the point is, so there are 2 points to make. One is if we had preferred bounded below complexes rather than bounded above, we would have gotten the opposite order on maps. And the second is that the order, what I call 1 and 2 here is totally irrelevant. The order is determined by the category, not by the indices. Okay, but that's a new phenomenon. When you diagonalize or when you talk about idempotent decompositions of categories, there's always a partial order floating around. Okay, so let me state the diagonalization theorem. And hopefully indicate the connection with Hilbert schemes. Okay, so what is this for? So the theorem is that, so I want to state it in some concrete level of generality that will certainly apply to Soergel bimodules. But it can also be restated in some larger level of generality, okay, that is not appropriate for a talk. So let A be the bounded above homotopy category of some category of bimodules. And suppose we have scalar objects, lambda 0 up to lambda r, so that each of them are invertible. And let's say alpha I plus 1 times the inverse of lambda I is supported in negative homological degrees. So there's some actual total order on the eigenvalues by homological degree. Suppose we're also given maps. It would be a crime if I didn't call them eigenmaps. So these are eigenmaps, which means something that I will mention in a moment. But these are just some given maps with the property that the tensor product of the mapping cones is contractible for all orderings of the factors. There's some technical stuff here having to do with commuting cones past one another. If this is the sort of thing that intrigues you, we can talk later. How do you prove that cones commute past one another? It's fine. And so what's the statement? Then there exist actual explicit complexes, Pi, what do I mean by explicit? I mean they're explicitly constructed from F and its eigenmaps. In other words, they're explicitly constructed from F and those maps. So they're no more or less explicit than F is. explicit complexes with the following properties. So first off, they're orthogonal. Secondly, they add up to 1, which again we know is kind of a funky relation. It's not, I don't want to literally say their direct sum is 1. So what's the kind of thing that I could put here? Well, I could put some iterated mapping cone, or some one-sided, I guess from yesterday we heard about one-sided twisted complexes in the sense of Bundel-Kapranov. So if you know what those are, that's what this is. But it can be expressed completely explicitly as just a direct sum with a twisted differential, meaning it's not the direct sum differential, but something more interesting, where the differential is, you take the differentials which are given to us from P, you put them on the diagonal, you do something on the lower diagonals, and then zeros everywhere else. So there's some differential of that form that connects up the P's to each other, so that the resulting complex is homology equivalent to 1. And these things are, projections onto the, they're sort of they're categorical eigenvectors or whatever. Okay, so that's the theorem. Diagonalization. So if you satisfy those things, then you're diagonalizable. Now I won't tell you what these explicit formulas are, but they're like, you take those pictures and you tensor together a bunch of them, and you get something that we prove are actual idempotents, and they add up to 1 in this way. And you have to wait till like Friday to see the actual picture, but or I can tell you what it is. Or you can do it as an exercise, because these things, these expressions categorify, so the PI categorify the Lagrange interpolation polynomials, whose definition I found on Wikipedia once upon a time. So they categorify these expressions. For each I, you take the product over all j's not equal to I of these expressions. And each factor you can categorify with something that looks like this. And then their product you categorify with literally the tensor product. And then you get the PIs. So that's what I mean when I say explicit. It's just an explicit thing. Okay, now let me state something which is not quite a corollary, but also involves a lot of hard work. This diagonalization theorem applies to the Soergel category. So this is maybe theorem 2. So for each T, which is a standard Young tableau of size on n boxes, sorry, I'm abbreviating, I'm trying to hurry, there exist these complexes, which are semi-infinite complexes of Soergel bimodules, and they categorify the Young symmetrizers. And they are simultaneous eigenprojections. So projections onto the simultaneous eigencategories. For L1, L2, L3, up to Ln. or these are the complexes of Soergel bimodules that they're Rouquier complexes for the Drusus-Murphy braids that Andre Nagutz talked about in his talk before this. And I'm sorry, I know I'm over time, but let me state one promising thing that should be thought of as, one thing that is maybe not clear from any of these talks is why there should be a relationship between the Hilbert scheme and Soergel bimodules. So let me say something but not write it, probably. So, as Andre mentioned in his talk, there are, to each fixed points in the flag Hilbert scheme, there are T of them, there are as many of those as there are standard tableaux. So to each fixed point, there's a skyscraper sheaf. And, conjecturally under this GNR correspondence, they correspond to, actually they don't correspond to the idempotents PT, they correspond to the finite idempotents, which I didn't have time to really talk about. But they're like finite versions of the PTs. And the endomorphism ring of PT itself is like supposed to be related to some coordinate ring of an open subset of the flag Hilbert scheme. And so let me just say vaguely this is related to F Hilb in some conjectural way, but precise. And we can actually prove this conjecture in at least two special cases. So for the one row idempotent, this is work of mine, categorifying. So these idempotents can be constructed independently of diagonalization for two special cases. And then, in this idempotent, I computed the endomorphism ring, and it agrees with the flag Hilbert scheme side. For this idempotent, me and Michael Abel computed the endomorphism ring, and it again agrees with the flag Hilbert scheme side. And then the theory of diagonalization actually produces endomorphisms. So these maps alpha, I'll just leave you with this last comment. If you have something that's diagonalizable, if you have something which is an eigen object for F, then any hom from 1 into F gives an endomorphism of P. So as soon as you have a hom from 1 into F, you tensor it with P, and you get a map from P to, FP, which is a multiple of P. So these endomorphisms that are coming conjecturally from the Hilbert scheme side are related to these maps alpha I in some very special way, which, sorry for going over. If you are curious about that, you can ask me later. Thanks.
More questions from the speaker?
Yes?
Sorry, you.
Oh.
Okay.
Could you do it if you have multiplicities?
You mean generalized eigenspaces?
Yeah.
Yeah, we don't know how to do that yet. Yeah. Well, I think what's lacking are examples, like nice examples of things that are like nilpotent operators or more interesting Jordan blocks. So far, all we have are the semi-simple guys.
I'm just going to comment. You talked about the full twist
Yes.
on strings. The eigenvalues of that are not sort of distinct on these
That's right.
ones, and you need the sum of the LIs to get
That's right.
distinct.
Yeah, that's a wonderful point. Thank you. So the eigenvalues of the full twist, which, by the way, so the full twist is, of course, this braid. I like to draw this picture, and I'm sad when I don't get to draw it. So that's the full twist braid. The eigenvalues of this thing, decategorified, are indexed by partitions. And then the eigenvalue itself is q raised to some power. That power is like the content of the partition. But many partitions have the same content. So there are actually multiplicities, and if you just write out this product over all partitions, there's some repeated factors, which is the thing you were mentioning. But you are saved by simultaneous diagonalization. The eigenspaces with the same eigenvalue corresponding to different partitions are sort of resolved by eigenspaces for smaller full twists. So the way you actually fix that is to not diagonalize each full twist separately, you kind of diagonalize them all at once.
Yeah, but if you diagonalize the sum of the L's, they've got distinct eigen.
Yes, that's right.
Which is maybe your tautological bundle in the other.
That's right, but we don't know how to construct that yet. Yeah, so that should be some chain complex of Soergel bimodules. It's not literally the direct sum anymore. It's some kind of iterated mapping cone. You know, in the same way that the tautological bundle is not, well, it has filtrations with subquotients, the LI, so it's not literally a direct sum in some sense. And we don't know how to construct that on the Soergel side.
It's not only that, but it seems in IKM construction, what you do is you invert quantities like 1 over 1 minus a monomial, whereas the eigenvalue of the sum of the LIs would not be a monomial. And
that one,
how to invert that?
That's right. So there's another issue, which is that our diagonalization theorem, as you may have noticed, I have to assume my eigenvalues are invertible. So in other words, I have to be dealing with invertible f's as well. And meanwhile, this guy you mentioned is not invertible. But I feel like we can fix that. Yeah.
Okay, so before we thank Matt for his nice talk, let me mention that actually this place is showing the formal dinner later. So there will be a formal dinner starting at 8:30.
7:30.
7:30, oh yes. Anyway, so let's thank Matt for the nice talk.